Welcome to Sundar's lecture. This is lecture number 62, and in this lecture we are going to see transient response of RL circuit for DC input, right? So, right, what are all the topics we have seen in the previous class? We have seen that inductor can store energy, and also we have seen that if you are giving a DC supply to the inductor, then current through the inductor will increase linearly. And then we have seen how long this current will increase. If it crosses the rated current, then inductor will be spoiled, right? Because it is increasing with respect to time, right? That is the expression we have seen. See, this is the expression. I of t is equal to V by L into t. If time increases, then obviously I of t will increase. With this basic knowledge, we have derived the energy stored in inductor, and we have got half Li square is the expression for energy stored in an inductor. Now, we will see how to cut off this linear increase of current in an inductor by doing a simple thing. And then we will continue with the RL circuit, right? So, first we try to get the basic knowledge when to stop this current, increasing current, right? So, that is this circuit. So, in this lecture we are going to see that, right? So now we have taken a circuit like this. See, consider a network. This is DC source. That is what we have given here. Anyhow, we are going to see for the sinusoidal input also, that we will see in the later lectures. So DC input has been given to a switch, and then it is connected to the inductor. Now, for example, case 1, what we will do, at case 1 we will take switch at position A. Switch at position A. So, if switch is connected to position A, then what happens? A DC supply is connected to the inductor. DC supply is connected to the inductor, right? So, what is the expression we know? So, VL, maybe I will take a different color. So, VL will be is equal to DL into DI by DT. This is the expression, and you see this voltage is directly connected across the inductor, and so this value will be 10. That should be is equal to, what is inductor value? It is 2, right? It is di by dt. And if you bring this 2 to other side, what you will get? Di by dt will be is equal to 5. And if you integrate on both sides, you will get this will be I. That should be is equal to I plus A, right? Because you bring this dt to other side and integrate on both sides, you will get I is equal to 5 plus A. What is A? What is this A? Maybe you make it as expression number 1. This A, which is nothing but it is a constant, right? It is a constant, integration constant. And how to find this A now? And you see, we will take I of 0 should be is equal to 0, which means this inductor is not connected to any other supply before closing this switch. That is very important. You should know what is the current through the inductor before you connect it to a DC supply. That is very important. But in this case, we assume that there is no current flowing through the inductor. Now, so what we can do now? So we know that I of 0 is equal to 0. So what you do, you put it in the expression. See, this is I of t. Wherever you see I, you try to defaultly understand that it is I of t, not just I, right? So you understand that. So if I of 0, then time is equal to 0, then this value becomes a 0, 5 plus A, right? I am just substituting the initial conditions, and this becomes now 0. This should be is equal to 5 plus A. Oh, sorry, I have missed 5t, right? This is if you integrate this one, what you will get? What you will get? So I will write it down. Anyhow, I have made a simple mistake. See, if you integrate this one, you will get phi t, right? Phi t plus a. Sorry, this one will be phi t plus a, because constant, if you integrate a constant, then constant multiplication of the base of integration, right? So it will be phi t plus a, and I of 0, we know that it is given as 0. So you substitute I of 0 here instead of this I of t. So it becomes I of 0 plus 5 into 0 plus a, and everything becomes 0. Everything becomes 0. This will be also 0, then a is equal to 0. So directly we can write it as I of t will be is equal to phi t. I of t is equal to phi t. Then if you draw the graph, even if you draw the graph, what you will get? So this is the graph, you take it as this is time axis and this is the current axis, and this may be 1, 2 seconds, 3 seconds, maybe 4 seconds, 5 seconds, and the current we will take it as 2, 4, 6, 8, maybe we should have 10 here, 10, right? So now this is the value. So if I put t is equal to 1 in this expression, what I will get? I will get around, it is 5 amperes of current. So maybe I will get around this point, from 0, and then if I put 2, then it becomes 10 amperes, right? Then it becomes 10 amperes. So now what I will take, the rated current of the inductor, whatever the given here, I will assume, not assuming, rated current of inductor is given as 10 amperes, right? It is 10 amperes. Let it be 10 amperes. Then after 2 seconds, it gets to the 10 amperes, right? Now what I am going to do, I am going to take it as case number 2. Case 2. Okay, in case 2, switch is connected at position B. Position B. I'm just taken the switch to A, that is already connected to A. Now I am just connecting it to B now, right? This point, this curve is now like this. It is like this up to point A. Up to switch is connected at point A. Yeah? Switch at A. That is the whole idea. And if it is connected to B, then what we have done? We have just short circuited this inductor, right? We have just short circuited this inductor. So what will be VL here? VL will be 0, because no voltage is connected and it is short circuited. If it is short circuited, then obviously voltage between 2 points will be 0. And it is now simple. What is that one? What is VL? VL can be written as what? Di by dt. Di by dt. And if di by dt is 0, di by dt is 0, there is no change in current, right? So that is the idea. No change in current. No change in current, right? Even if you integrate this one, what is the initial condition we should have? Initial condition is I of, now I of 0 may be initial condition, which is equal to what? Which is equal to 10 amperes. Right? That is what we have seen here. At 2 seconds, I am just doing this at 2 seconds. At t is equal to 2. That is the idea. So this value will be like this, and then there is no change in current. That is the given idea. That is what we have got from this expression. So if you short circuit this one, then after 2 seconds there is no change in current, and this 10 ampere will be hold. 10 ampere will be hold throughout forever in the inductor. That is the idea, right? This is after switch at B, connected to B, right? So current in the inductor will be now, it is 10 amperes, obviously that will be hold. And now we try to find what is the energy stored. What is energy stored? What is energy stored now? So it will be W, which is equal to half Li square. Now what is the value? This is 1 by 2 into, it is 2 Henry. So it will be 2 into I is 10 amperes. So it is 10 square. So 2 will be cancelled out, and finally what we will get? It is equal to 100 joules, right? So what we have done now, we have connected a 10 volt source to the inductor. After 2 seconds, I'm just considering the rated current of the inductor is 10 amperes. That is what I have written here. So at t is equal to 2, I will get 10 amperes of current. Then obviously I close the switch to position B, and now the inductor is short circuited. And if inductor is short circuited, then VL will be is equal to di by dt becomes 0. If di by dt is 0, then obviously everybody knows no change in current. So what is the initial condition? That is 10 ampere. That 10 ampere will be hold. And now if you are going for energy stored in an inductor, then half Li square, you substitute 10 amperes, then you will get 100 joules. Now what we have done, we have pumped 10 amperes of current into the inductor, and we have stored 100 joules of energy inside the inductor. Now this 100 joules of energy can be retrieved if you connect this inductor to a resistor here. Then that resistor will get the energy. It is transferred. That we can do. So in small circuits, if you want to store energy, then we can use inductors. That is the whole idea, right? Now what we will do, we try to find, and then now you see we are connecting this to a short circuit, and then we are doing so many things to store energy, but it is not necessary. Put a resistor in series with the inductor, and then you see we don't need to short circuit this inductor after the rated current, and it is not necessary. We can put an resistor and we can do it with a simple technique, right? That we will do now, that we will see now, right? And now you see we have taken a circuit with a resistor connected, and a switch in the previous case, the same diagram but with a resistor now we have taken, and now this is the RL circuit. This is the RL circuit. Anyhow, see, first I will take case number 1, which is connected to position A. So if it is connected to position A, then the voltage source E, a resistor and an inductor is connected in series. Right? So now you apply KVL. Apply KVL. Right? This will be now I of t. Right? That is what we have taken it as I of t. And if you apply KVL, so what you will get? So it is E minus I of t into RT. I of t into R. Then it is traveling from plus to minus, right? What is the voltage across the inductor? It is L into di by dt. So it is minus minus L into di by dt. That should be is equal to 0. And you can simply write it as E will be is equal to I of t into R minus plus L into di by dt. See, this I, you just write it as I of t. Anyhow, I have already told you, you just try to write I as I of t. So this is equation number 1 now. And now you see what I am going to do. I am just going to solve this equation. This is actually first order differential equation, right? We have di by dt inside this. So this is the first order differential equation, and try to understand me. I am going to multiply with the integrating factor. I will tell you why I am doing these kind of things after. So first, before that, I try to divide L on both sides. I will tell you what is this integrating factor, and you see these kind of things we are going to eliminate. That is why I've told you I'm going to explain you how to solve the differential equations in my future lectures. I will give you tips, easy tips to solve the differential equations. Anyhow, so this will become now E by L, which is equal to I into T R by L plus this L and this L will be cancelled out because you will have like this, right? So di by dt. And now I am going to multiply it with integrating factor. Integrating factor. You see these kind of things you can easily find it from the internet anyhow. It is nothing but e power r by L. So this is the integrating factor. Power r by L into t. That is the integrating factor. That is what I am going to multiply on the both sides. So maybe I will write it down in this way. This is di by dt into e power r by L into t plus I of t into r by L. Here also you will have e by L t, e power L by t. Then this will become now e power r by L t into e by L. So this is the value. And now you see I can write it as di by dt into, and you see you can write like this because you see this is actually uv, and the differentiation of you have to keep this one as it is, and you are differentiating this I of t, that is what this expression, and you have to keep I as it is, and then you have to differentiate this one, so r by L into e power t. So so these two terms I have written this with uv formula, just uv formula. I have applied uv formula and I will get like this now. This is the thing, right? So after this, now what you do, you integrate on both sides. So if you are integrating on both sides, integrate on both sides. So I will directly write integrate on both sides. What you will get? What you will get, this integration, this dt will be cancelled out. So it will be e power r by L into I of t. That should be is equal to, see this e by L is a constant one. So you take it outside. And if you integrate this one, what you will get? E power r by L t divided by it will be r by L plus a. It is a constant, right? Because we are integrating without any limit, so it will be constant. So now if this one and this one can be cancelled out, and if I bring this e power r by L by t to the other side, so I will finally get, see, I of t can be written as, so this one e by r is there, this e by r, and if I bring this to this side, this term will be cancelled out, right? This e by r and e power t, everything will be cancelled out. So plus a divided by this term will come, so I will just bring it to the numerator, so it will be e power minus r by L into t. So this is the formula for I of t. This is the formula for I of t, right? So what we can do now, we try to substitute t is equal to 0 and t is equal to infinity in this expression. So before that, what we do, we try to get what is the value of a. So late I'm just assuming that I of 0 is 0 in this condition. So I of 0, I'm just taking it to 0. So what I will get, initial, if I'm just considering that there is no current flowing through this inductor before I'm closing this switch. That is this condition. And I will get I of 0 should be is equal to 0. Then this should be is equal to e by r plus a e power minus r by L. And then this becomes now 0, right? If it is 0, then this term everything will become 0, right? Everything will become 0, and it will be e by r plus a is equal to 0, and it will be a is equal to minus e by r. This is the initial condition. This is the value of a, right? If you are substituting initial condition, then this will be the value of a. Then what happens to the I of t? I of t can be written as e by r minus e by r e power minus r by L into t. So this is the final expression for I of t. So you see this expression can also be right. So I will write it in the next page. So this expression I of t can be also written as you take e by r commonly outside. So you will get 1 minus e power minus r by l into t. So this is the expression. See, I have just taken e by r outside. So now my aim is to draw the graph. Draw the graph maybe. My aim is to draw the graph. This is I of t maybe. This is time axis. And now what I want to do, t is equal to 0, right? You substitute t is equal to 0, make it as expression number 2 into what you will get if you substitute t is equal to 0, then I of 0 will be is equal to e by r into 1 minus e power. See, if I put t is equal to 0, then every expression becomes 0 here. So all it becomes 0. So it is e power 0. What is e power 0? It will be 1, right? It may be minus 0 or it may be plus 0. What it becomes? It becomes 1. Then the whole expression becomes what? E power 0 will be 1. So this will become 1. So it becomes 0. That's all. That's all, right? So it becomes 0. And if I want to put what is the value of infinity, maybe I will write it here at t is equal to 0. At t is equal to 0, what happens to my current? It is also 0. It starts at 0. And if I put t is equal to infinity, if I put t is equal to infinity in expression number 2, what I will get? I of infinity will be is equal to e by r into 1 minus e power minus infinity, right? So everything becomes infinity if you put t is equal to infinity. So what is this value? This value will be 0. Now we know that e power infinity will be 0. So what is the final answer? I of infinity will be is equal to what? It is e by r. It is e by r, right? So maybe you see this curve will come like this. At t is equal to 0, then at t is equal to infinity, this curve will looks like this one. So this point, which is nothing but it is e by r. This point, which is nothing but it is e by r. So this is why we need to put infinity in t is equal to infinity to get this value. See, you don't take infinity time to go to this point. E by r will be reached at some instant. For example, we will take tau is equal to, maybe this is the time constant value, tau is equal to L by R. This is the time constant of RL circuit. I will tell you why it is actually time constant. It is R by L, L by R. So you substitute this value in the expression I of t, what you will get? I of t is equal to E by R into 1 minus e power, it is minus r by L is there, and just I am substituting t, instead of t I am just substituting r by L by r. So I will get like this, right? So this value will be fully cancelled out. It will be minus e power 1, and if you simplify this, then it will be 0.632, right? Value. You just simplify this one, what you will get? I of t will be is equal to 0.632 into E by R. This is the value you will get, and which means you will get 63 percentage, right? 63 percentage. Maybe at this point, if it is tau is equal to L by R, then this value which is nothing but it is 0.632 into E by R. So at tau time constant, you will get 63 percentage of E by R. Then if you are going for another tau, maybe this time can be like in this point, then you can find what is E by R. So you can obviously find at what time E by R will be the final current. It is not necessary, it has to get to infinity time for getting the E by R. Don't think like that. It is not like that. you will get E by R at some instant, maybe at some stipulated time, a very long period. Maybe you take like that, a very long period, right? So this is how we are getting these values. Now, in the next class, what we will do, see now, if it is connected to this one, then the E by R current will flow through the inductor. After a long time, it becomes E by R. That is the whole idea. And you see, if it is so, then this resistor will lose power, right? There is a power loss. Then what we will do, just you put this S to the B, then E by R current will always flow through this inductor. That is what we have seen in the previous one. After connecting this one, so this 10 ampere will flow for a whole period. That is what we are trying to do here also. So without power loss, this inductor can store E by R current forever. Right? You can switch this in, switch to the point B, switch to B. Maybe this is case number 2. Then what happens? Di by dt will be 0 and inductor will carry I of t will be E by R forever without loss in inductor, without a loss in resistor. Since if it is connected like this, then there will be some drop across the resistor. Why it is needed? Even though the inductor will get E by R, right? But once this inductor carries E by R current after a stipulated time, if you connect the switch to point B, this inductor will carry the E by R current without the loss in the resistor. So now you see inductor can store energy, and you see you can also, I have already told you, here we have taken current as 10 amperes. So here, if what is the inductor rating? What should be the inductor rating? E by R. That is the current. Finally, that current is flowing, right? That current will flow, and you take inductor current rating can be what? Can be what? E by R. See, we are getting so many points using RL circuit. You don't know here, right? We ourselves know that it is 10 amperes, so we are switching the inductor, we are switching the switch to the point B at t is equal to 2, so that 10 amperes will flow, and there are so many risks in this one. But once you know what is the rated current, depends on the rated current and the you can put the voltage and resistor. If you know my voltage is 10 volt, then what is the rated current of the inductor depends on that. You put resistor value. You put resistor value, that is the final current will flow through the inductor. Very simple, right? There are so many things we have discussed in this class. Any of this class is lengthy one. You try to get the knowledge, and we will go for the capacitors in the next class, right? We will see that in the next class. Thank you.